Hiya folks, this is question 7. So part A is like something you would have seen in junior cert almost. So it's we're going to get she pays 20% on the first 40,000. So we're going to do 40,000 multiplied by 0.2 or multiplied by 2% percentage button on calculator. That's 8,000. And then we're going to do the other 14,000. That's the 54,000 that she earns minus the 40,000. That we've already paid it 20%, so we're going to multiply that by 0.4, and that would give us 5,600. And then I'm going to do those two added together, 8,000 plus 5,600, and that gives me 13,600. So that's the total tax that she has to pay. To pay all of it, but we can subtract a tax credit. So it says that her tax credit is 1,775, so she doesn't have to pay as much when we take away the tax credit. So it's 11,825. That's the actual amount. That's the net tax that she has to pay. And then we're just going to do the salary from the start. So the 54,000 take away 11,825, which we got, and that gives us the amount she takes home. So that's 42,175. Right, part B, we have to use the compound interest formula. So the compound interest formula is F is equal to P times 1 plus I to the power of T. So P is the present value, or the amount you're putting in at the start, I is the interest, and T is the time. So we're trying to find P in this case. So if I was to rearrange it around that before we start, it is, I could just move the 1 plus I to the power of T over, so 1 plus I to the power of T, because they're asking us to find the present value or the principal amount in this question. So if I just fill it into the formula, then the final amount is the 164.75. That's the final amount. 1 plus the interest. Now the interest, it's 0.279%. So as a decimal, that's 0.00279. So be careful. That's what it is as a decimal. So 1 plus 0.00279, and that's all to the power of time. So the time, then we need to do it for the first 3 monthly repayments. So the first repayment would just be all of that to the power of 1. So that's the first one. So I'm going to get the second one and the third one here then. So the second one then would just be the same thing, but the power is just going to become a 2. So 164.75 over 1 plus 0.00279 to the power of 2. And then our third one is going to be the same thing, but with a 3 there. Now I could do the 1 plus bit there in the brackets if you want. Right, next part. Right, here then we're trying to figure out how much she borrows for her mortgage. So it's going to be all of these added up, really. It's going to be all of those added up, but we need to keep going, and we need to get to the 300 one, because it's going to go over 300 months, because it's 25. It's a 25-year mortgage, so 25 times 12 is 300. So it's a geometric sequence, really, and we're going to use the sum of geometric sequence eventually here. So our first term is, so with a geometric sequence, S of n is equal to and you have to go to your log tables. So we want the sum of the first 300 terms, so it's S of n we're using, it's this formula. So it's A and then 1 minus r to the power of n over 1 minus r. So it's that formula. Now A is going to be the first term, so A would just be the first term up there that you can see. So remember first, second, third terms. So A would be just the 164.75 over 1 plus 0.00279. That's our first term. R would be what it's being multiplied by each time. So if you think about it, to get from the first term to the second term, we're multiplying the bottom basically by 1 plus 0.00279. Each time we're multiplying the bottom by that. So overall we're multiplying by 1 over, I'll just say 1.00279. I'm just adding the 1 to the 0.00279. Yeah, that's what R is. And then our n here, we're looking for the sum of the first 300 terms in that sequence. So we're looking for them all added together. Right. Let's just try and put in everything then, so it's going to be awkward obviously. So what I'm going to figure out what the top is there first. So yeah, our A, I'm just going to do 164.75 and I'm going to divide it by 1.00279 and that'll tell me what A is, and I'm just going to put it in here. So that's 1643.165 568. So that's A. I'm going to multiply that by 1 minus what R is. R is 1 over 1.00279. Here are exceptionally awkward in this one, so just be really careful, be nice and neat with what you're doing. And then same thing again, 1 minus 1 over 1.00279. That should be to the R there should be to the power of 300 as well. So try to sneak that in there. Yeah, that's really what it should look like. Alright. And so easiest thing is to put it all in the calculator together. You might have to break down some of it first. But it should work on your calculator. So 334.563. So it's correct to the nearest euro as well. So that's it. Right, so first part of part C then. So now we're getting on to differentiation. So we're just going to, all you have to do here is differentiate that. So we're getting f dash t. So remember, the differential of e to the x is just e to the x, but we have to use chain rule in it. So it's just going to be 5,000 e to the power of 0.04t, but then you have to multiply everything by the differential of what is in the power up here. So the differential of all of that would be 0.04. And then simplified, you can do 0.04 multiplied by the 5,000, and that will give you 200. And then e to the 0.04 t. Now we need to find the rate at which the amount of money in the account is increasing after 3.5 years. So I'm just putting in 3.5 then in for time. So f dash 3.5 would be 200 e to the power of 0.04 times by 3.5, and that will give it to me. And you put that in the calculator, and I got 230. And that's to the nearest euro. They want it rounded to the nearest euro again. Right, second part. Yeah, now this is average. So when you see the word average there, it should jump out at you. It's very important. So it's average. We're using the average integration. So we're just going to be integrating it, but you have to do 1 over b minus a first. And then it's just the integral of f of t. And to dt. So now it's the first 5 years, so it starts at year 0 and then it goes to year 5. So it's going to be 1 over, so b will be 5 and 0 will be a. So 1 over 5 minus 0, the integral of 5,000 e to the power of 0.04 t. So now integration again, when you integrate e, it's going to be the same thing, but we have to divide by the differential of what's in the power, the opposite of what we did the first time. So 1 over 5, and then it'll be 5,000 e to the power of 0.04 t, but we're dividing by the differential of what's in the power, which would be 0.04, the opposite of the first time. And that's it. So that we have to put in a 5 and put in a 0 then for t. Right, so 1 over 5 so we're going to subtract then, and we're going to put 0 in for t. Now I could have simplified the numbers there first of all. I probably should have done 5,000 divided by 0.04 and got something that would have made it a little bit easier to write out. So obviously then that will become a 1 there. And it's a fifth times all of that as well. Now I should really have multiplied the 1/5 in, it would have made things easier, and divided to 0.04. So you can break it down a little bit more there if you want, but that's basically it anyway. You can probably get all that into the calculator together, and then your final answer is 5535. That's it. out the last bit. So what's happening is it's going up. So if you examine the function there, like the initial amount, it's going up. So when t is 1, so obviously when t is 0, we just have 5,000. But then when t becomes 1, so 1 year, it's going to go up by, it's going to be multiplied by e to the power of 0.04. So, and then it gives you whatever that will be then. So e to the power of 0.04, that's the common ratio here, and so on. So e to the power of 0.04, so really e to the power of 0.04 would be 1.0408. So the percentage really is 0.0408. So, that's what is a decimal. So as a percentage, then we have our answer as a percentage. It's just 4.08. So it's kind of picking out really that it's going to be the e to the power of 0.04 and figuring out kind of what that is percent. So really that's all we have to do there.